Hello everyone, in this lecture we will see the numerical on magnetic and dielectric materials and the stepwise solution of the same. I have taken the numericals from the end semester examination question papers of the year 2017, 2018 and 2019. The main aim here is to take out the fear from your mind while to attempt the questions, that numerical questions in end semester examination. But as per my view, why not? As these basic concepts we have already learned in 11th, 12th and also in first year, then it is very easily possible to solve these numericals with proper understanding. If the understanding is good, then we can easily solve these numericals, right? Let us begin with the first question of the year 2017. A magnetic field strength of a material is 1 into 10 raised to 6 ampere per meter and its flux density is 1.8 Tesla. Calculate its permeability, magnetization. Now the best practice is to write the given data first. So here in question it is given field strength of a material, that is H is equals to 1 into 10 raised to 6 ampere per meter. Then flux density B is equals to 1.8 Tesla. After the given data, write down what to find. So here as per the question we have to calculate the permeability mu and magnetization M. Now with this given data and to find, we can write down the equations to be used. So by which equations we can find out this permeability and magnetization. So now we will continue this. So here to find out the permeability mu, we must know the relationship between the flux density and field intensity in magnetic circuit. So B is directly proportional to H. So the equation is B is equals to mu H. Now to find out the relative permeability, we must know mu is equals to mu naught mu R. That absolute permeability is equals to the product of permeability of free space and relative permeability, and the value of mu naught is equals to 4 pi into 10 raised to minus 7 henries per meter. Next is magnetization. M is equals to in bracket mu R minus 1 multiplied by field strength or field intensity H. Now just by using the equation and putting the values, we can get the answer for permeability. So here from the equation B is equals to mu H, we can write mu is equals to B by H. So put the value of B as 1.8 Tesla and the value of H 1 into 10 raised to 6 henries per meter, and we will get the answer mu is equals to 1.8 into 10 raised to minus 6 henries per meter. Now to calculate the magnetization, we must know the mu R. So by putting the value of calculated mu and the value of mu naught, we can get the mu R. So mu is 1.8 into 10 raised to minus 6 as per our calculation, and mu naught is 4 pi into 10 raised to minus 7. So the calculated value of mu R is 1.43239. It is a unitless quantity. Now again we will continue. Now here magnetization M is equals to mu R minus 1 multiplied by H. Now put the value of mu R here and H. Then the final answer of magnetization is 432390 in amperes per meter. Let us see the next question of end semester examination of year 2018. In a material, an application of magnetic field of 1.75 into 10 raised to 5 ampere per meter causes a magnetic flux density of 218.2 milliweber per meter square. Calculate its permeability and susceptibility. Also find magnetization. So first write down the given data. So as per the question, magnetic field, that is field strength, is given 1.75 into 10 raised to 5 ampere per meter, and flux density is 8.2 milliweber per meter square. So convert it into Weber per meter square. That is 218.2 into 10 raised to minus 3 Weber per meter square. Then after that write down what to find. So here as per the question we have to find first permeability, then magnetic susceptibility, and then magnetization. With this given data and what to find, we can write the equations to be used. So to find out or to calculate permeability, susceptibility and magnetization. So here we will continue with the equations to be used. So the first equation to be used, as we have seen earlier, B is equals to mu H, then mu is equals to mu naught mu R. Mu naught is equals to 4 pi into 10 raised to minus 7 henries per meter. Then susceptibility is equals to mu R minus 1, and magnetization M is equals to mu R minus 1 multiplied by H, right? That is the product of susceptibility and field strength. Then just by using the equation and putting the values, we can get the answer. So from the equation B is equals to mu H, we can get the mu. So put the value of B and H here. So the final answer of mu is 124.685 into 10 raised to minus 8 henries per meter. Then to calculate the susceptibility, we have to find mu R. So get the ratio of mu by mu naught. So put the value of calculated mu and the value of mu naught. So the answer of mu R is 0.992211. Now continue to this. Find out the susceptibility. X is equals to mu R minus 1. So put the value of mu R as 0.992211 and minus 1. So the final answer of susceptibility is minus 7.789 into 10 raised to minus 3. Why it is minus 7, that we'll see. Then magnetization, M is equals to mu R minus 1 multiplied by H. So put the value of relative permeability mu R and field strength H. So the final answer of magnetization is 1363.075 ampere per meter. So these are two simple examples of the magnetic materials to find out the permeability, magnetization and susceptibility. Okay. Now let us see the next question of end semester examination of year 2018, and that is of dielectric materials. So the question is, two parallel plates 0.15 multiplied by 0.30 meter square in area are separated by dielectric of thickness 0.06 meter. Dielectric constant epsilon r equal to 5.4. Capacitor so formed is connected to a 400 volt DC supply. Calculate induced polarization in dielectric and electric field intensity in the dielectric. So as we know that, first write down the given data. So as per the question, the area of the two parallel plates is given as 0.15 multiplied by 0.30 in meter square. Then the dielectric thickness D, small d, equal to 0.06 meter, that is the separation between two plates. Then epsilon r, relative permittivity, is 5.4 and applied voltage V is equals to 400 volts. Then write down what to find. Here as per the question we have to find polarization in dielectric, and that is noted by capital P. Then electric field intensity is noted by capital E. Now with this given data and what to find, we can write down the equations to be used to find out polarization and electric field intensity. So the equations to be used to calculate the polarization P is equals to epsilon naught E in bracket epsilon r minus 1, and the next equation is epsilon is equals to epsilon naught epsilon r. The value of epsilon naught is 8.854 into 10 raised to minus 12 farads per meter, and relative permittivity can be found out by taking the ratio of epsilon and epsilon naught. Then the next equation is electric field strength equal to V by D. V is the voltage, D is the separation between two parallel plates. So just by writing the equation and putting the values, we can get the answer. So here, putting the value of voltage and distance between the two parallel plates, the answer of electric field strength is 6666.667 volts per meter. Now with the value of calculated electric field strength, then relative permittivity and permittivity of free space, calculate the polarization. So here put the values of epsilon naught, calculated E and epsilon r, and the final answer of polarization is 2.59717 into 10 raised to minus 7 coulomb meter. So the unit of polarization is coulomb meter, as it is expressed in the unit of dBi. So the unit is coulomb meter. Now what is polarization? We know that a dielectric consists of molecules, the atomic nuclei of which are effectively fixed relative to each other. So in the absence of any external field, the electrons are distributed symmetrically around the nucleus at any instant. When an electric field is applied, the electrons of the atoms are acted upon by this field, and this causes a movement of the electrons which are displaced in a direction opposite to that of the field. This movement is opposed by the attractive forces between nuclei and electrons. So what? This moment is opposed by the attractive forces between nuclei and electrons. The resultant effect is to separate the positive and negative charges in each molecule so that they behave like electric dipoles. The strength of each dipole is given by the dipole moment, which in its simplest form consists of two equal point charges of opposite sign separated by distance. So the dipole moment has a magnitude of the product of Q and D and is represented by a vector pointing from the negative charges in the direction of the positive charges. So generally the direction of the dipole moment is parallel to the direction of the applied electric field. That's why the dipole moments are expressed in terms of the dBi unit, and that is coulomb meter. Right? When the dipoles are created, the dielectric is said to be polarized or in the state of polarization. When the field is removed and the atoms return to their normal or unpolarized state, the dipole disappear. Right? So this is the polarization. Now we'll see the next question, that is from the end semester examination of year 2019. And the question is, in a material, an application of magnetic field of 2.75 into 10 raised to 6 ampere per meter causes a magnetic flux density of 0.2485 Weber per meter square. Calculate its permeability and susceptibility. So first write down the given data that we have seen earlier. So as per the question, magnetic field, that is field strength, H is equals to 2.75 into 10 raised to 6 ampere per meter is given. Then magnetic flux density B is equals to 0.2485 Weber per meter square. Then write down what to find. So here, as per the question, it is asked to calculate permeability mu and susceptibility. So with this given data and what to find the mu, the equation is B is equals to mu h, and to find out mu r, use the equation mu is equals to mu naught mu r, and to find out the susceptibility, use the equation mu r minus 1. So just put the values in equation mu is equals to B by h, and to find out the mu r, put the value of calculated mu and mu naught. Then put the value of mu r in the equation of susceptibility, x is equals to mu r minus 1, and get the value of susceptibility. Here the susceptibility is negative. Now we will see why the susceptibility in some cases positive and in some cases negative. As we have seen in above examples, the calculated susceptibility is positive or negative. So to justify this, let us see the susceptibility of some paramagnetic materials at room temperature. So here the first column is of material, then the second column shows the susceptibility x is equals to mu r minus 1, and the third column is relative permeability. So here the relative permeability is 1. As for many applications in electrical engineering, it is a good approximation to take the relative permeability of paramagnetic substances or materials equal to unity. Right? Now why the susceptibility is positive here? Since paramagnetism requires the existence of permanent dipole moments, paramagnetic susceptibility may be considered to be analogous to orientational susceptibility associated with dielectrics. That's why in paramagnetic susceptibility as well as in orientational susceptibility, the susceptibility is positive and temperature dependent, and therefore the paramagnetic susceptibility varies inversely with the absolute temperature, and this is the Curie law of paramagnetism, right? And that's why for large fields at low temperature, the magnetization is no longer proportional to the field and tends to a constant value, and therefore paramagnetic materials have a small positive susceptibility of the order of 10 raised to minus 3 at room temperature, which is much larger than negative contribution due to the diamagnetic effect. Okay. Similarly, to justify why the susceptibility is negative, let us see the susceptibility of some diamagnetic materials at room temperature. So here from this table it is clear that the susceptibility is negative, that is x is equals to mu r minus 1, and the relative permeability of the diamagnetic material is given approximately by mu r is equals to 1 minus 10 raised to minus 5, that is 0.9. So that for most electrical engineering applications, the permeability of such material may be taken as equal to unity, right? As we know that the magnetic moments of diamagnetic materials are mainly due to the orbital angular momentum of the electrons. A steady current flowing in the orbit produces a magnetic field equivalent to that set up by a dipole perpendicular to the plane of orbit, right? So from Lenz's induction law, the induced magnetic field will cause change in the external magnetic field, that is the induced magnetic moment will be negative. So a material in which an external magnetic field produces a resultant moment in the opposite direction is called diamagnetic, and in such materials the magnetization in opposite direction to field strength, and as a consequence the susceptibility is negative. The diamagnetic susceptibility is very small and negative as from this table, right? And why? Because it is observed that in the repulsion experienced by diamagnetic materials when placed in a magnetic field. That's why, since the susceptibility is determined by the electron structure of the system, So it does not depend on external conditions such as temperature, right? So that's why in diamagnetic cases the susceptibility is negative, and in paramagnetic materials the susceptibility is positive. Okay, so that's it for this lecture. If you have any question or any suggestion regarding this, so let me know. Thank you.